All right, but for now, we're talking about derivatives a little bit more, and then we're going to go on to something completely different, maybe probably next time. Derivatives for non-regular languages. This is what we started talking about before the test a little bit. Derivatives for proving a language is not regular. I will try to refresh our memory. I hope you remember what the derivative is. There was no question about the derivatives on the test, just because we hadn't really discussed them in very much sophistication, so there wasn't a lot to say about them. Any question I could have come up with would have been very easy, and I just decided not to do it. But derivatives, remember, like the derivative with respect to A, it means you look at all the words in your, all the strings in your language which start with A, and you remove the A from them at the beginning. Anyway, the point of derivatives, as far as we're concerned, is that you can use derivatives to prove that a certain language is not regular. And here's the theorem that we discussed, I believe, a week ago today, the time before the test. The big theorem about derivatives and why we care about derivatives, it says if L is a regular language, if L is regular, then there are only finitely many derivatives. What I mean by that is when you take, say, the derivative with respect to A, or the derivative with respect to B, or the derivative with respect to AB, or BA, or anything, no matter what kind of derivative you do, you can only get finitely many different answers from taking the derivative with respect to whatever, all right? Even though there are infinitely many different ways you could do the derivative with respect to different strings, all the answers are going to be the same. There's only finitely many different answers you can get, all right? You cannot get infinitely many different derivatives from a regular language, okay? And usually the way that we use this is actually the contrapositive of that. The contrapositive, which is equivalent, would say if L has infinitely many derivatives, then L is not regular. All right. By the way, a little linguistics language. I hope that you, like me, say finitely many and infinitely many, rather than just the word infinite. My kid was talking about this. My kid who's in 9th grade said, my math teacher said something wrong. My math teacher said there are infinite numbers. What she should have said was there are infinitely many numbers. And I said, I'm proud of you, kid. There are not infinite numbers. Like each individual number is not infinite. There are infinitely many numbers. This is a little math pro tip. You sound foolish when you say there are infinite numbers. What you mean is there are infinitely many numbers. All right? Unless you're actually talking about like transfinite arithmetic. There is such a thing as different sizes of infinity, and you could consider those things to be numbers. That's not what she meant, though. Come on. All right. Anyway, if a language has infinitely many different derivatives, then that language is not regular. So the standard example is this language. This is everybody's favorite language, favorite non-regular language. This is kind of the simplest example of a non-regular language. A to the n, B to the n. I guess I should write this as a set. All right. This is not regular, since I can do the derivative with respect to a to the I. So I can imagine doing the derivative with respect to a, and then also the derivative with respect to AA, and then also AAA, all right? And each of these derivatives, when I do this to L, D with respect to a to the I, that means I'm going to cancel out the first bunch of A's on the beginning, but only I of them. So this gives the language a to the n minus I, b to the m, right? You just cancel out some of the A's on the front. Not all of them. You cancel out the first I of them. And this, actually, I'm going to call this, sorry, I should have, sorry to squeeze that in. I meant to write it this way. Let di be this language, that derivative. So depending on what I is, you could do d1 is the derivative just canceling one a, d2 would be canceling two a's. But the answers are going to be different every time, right? d1, like I said, is when you cancel out one of the a's. That's different from if you had canceled out two of the a's, and so on. So these are all different. And there's infinitely many of them because the I could be anything, all right? These are all different, so L has infinitely many different derivatives, which means it must be not a regular language. So L is not regular. That's that. All right. This was I did exactly this example last time on Wednesday of last week. So this is the end of the refreshing your memory about what we've done already. All right? That is not a regular language. So when it's your job, you're going to do this often on the homework and I suppose on our next test. I will give you an example language and say, show me that this is not a regular language. You have to, this is usually not very difficult, but you have to think of how am I going to take the derivative in infinitely many different ways and get a different answer every time, right? In an example like this, I decided to just take the derivative with respect to a over and over again, different powers of a. But sometimes it's more interesting. You have to figure out what exactly are the derivatives that I should be using to make it so that the answer is a different answer every time. That's the idea. Well, I just wanted to do a bunch more examples today. I got some for you to try eventually, although I'm not sure if we're going to get that far, but we'll see what happens. Let's try this one. This is very, very similar. A to the n, b to the n, c to the n. This one also is not regular. So let's show it's not regular. Again, you have to decide what are the derivatives that I'm going to use so that I get a different answer every time. And actually, in this case, you can do exactly what we did last time. You should be looking at the fact that these strings here, they all begin with a bunch of a's. And if I take the derivative of those, it will cancel out some of those a's. And depending on how many you decide to cancel out, you're going to get different answers every time. So that's the idea. So I'm going to say, let di, again, this will look exactly the same. And this time, what is the format of the string after you cancel out a bunch of a's at the beginning, I of the a's? You're just going to get a to the n minus I at the beginning, but still ends on the b's and c's. That's because this derivative cancels some a's at the beginning, leaves everything else the same. All right, and you just have to say, these are all different. I mean, when you choose different values for the I equals 1 or 2 or whatever, you're going to get different answers over here. Because when I equals 1, it means there's one less A. When I equals 2, there's 2 less A's, 2 fewer A's. I should say fewer in that situation, since I'm being picky about language. All right, these are all different anyway. So that means L is not regular. Infinitely many different derivatives. All right. Yeah.
Why doesn't that work with like a to the n? Why doesn't that have infinitely many derivatives?
Yeah, actually, I was just about to say, what happens if the language is actually regular? You might think like, can you just do that for any language at all, even if like regular or not? What's the big deal? What's the difference? Check it out. Let's see. What if L actually is regular? For example, how about a to the n, b to the m? This one actually is a regular language. You can do a regular expression for this would just be, can anyone give me a regular expression for that? Do you remember regular expressions? Yeah?
A star, B star.
Yeah, A star, B star. This is just some number of A's followed by some other number of B's. Now, if it's the same number, then you got problems. But the N and the M being different makes it very easy to handle with a regular expression. Anyway, let's try the same thing. I go di equals derivative with respect to a to the I of L, which is a to the n minus I, b to the m. This is very subtle. Aren't those all different, just like in all the other examples? These are all different, is what I said, because if you use different values for the I, you get different things here. Actually, it's not so. In this example, these are not all different. Anybody agree with that? Anybody have anything to say about this? This is actually something that came up on the previous homework assignment. I don't know if you noticed. These are not all different. Anybody agree? In fact, they are all the same. Yeah.
Well, because, like, for instance, because the B doesn't change, it's just like if you're adding an A on, but then you could always just add another A, so it's all the same, even if you're just, like taking away as many as you want.
Yeah. What I see here is like you might say, well, these are different because you took away some A's, but actually, this still can just be any number of A's and any number of B's, right? Because there's no relationship between these two exponents, there's no difference between writing a n minus I here versus if I had just written a to the n. These are the same. These are all equal, actually, to a to the n, b to the m. Because you have to just think about what this means. It means some number of A's followed by some other number of B's. And it might be the same number. And what does this mean? Well, this also means some number of A's followed by some number of B's. Now, you can imagine that this is actually less A's than it used to be, but it doesn't matter. It's still just some number of A's followed by some number of B's. These are all equal to this, which in fact is the same as L, right? That's what L was originally. So in fact, in this particular example, L only has one derivative, no matter what derivative. Well, actually, you could get the empty set if you did dB. You might, yeah, you would get some bunch of B's. It doesn't have only one, but all of these derivatives in any case are all the same. All right, even though when you write it as a set, it looks like maybe these are different from each other. They're not. So it seems very simple on the surface, although there's some subtlety that you have to think about. Any thoughts about that? Let's just try some, yeah.
Do we have to put the minus I for the derivative?
Here?
Yeah.
Well, you probably should. I mean, it is a fact that in this example, that is the same as that. But it's not immediately obvious, I would say. And for example, up here, this is not the same as that. And the difference is because this exponent is actually related to the other two. And in this set, it says we have I fewer A's than there are B's. But this doesn't mean that. It's I fewer A's than something else. It's not. It has nothing to do with the B's here. All right. So I would say you probably should write it here because it would be confusing to immediately write that again. But anyway, the moral of the story here is if it's a regular language, then actually you're going to get the same answers every time for the derivatives. All right, I got a few more slightly weirder examples. I would say these examples all so far have been very simple. How about, here's another one that's fairly simple. BA to the power n followed by AB to the power n. This one is not regular. Your job is to show it's not regular. How do you do that? I mean, really, would you mind if I say, we're really writing like a little proof every time, although in these examples, the structure of the proof will be basically the same every time. You always just say let di equal, and now you have to decide for yourself what are you going to put here to make it so that you get a different answer for the derivative every time. And it will involve some i's, usually a power of I, but I mean, anybody have an idea here? in the past we've been using a to the I. The reason that I always use a to the I is because I'm trying to, what the derivative does is it cancels stuff at the beginning. And these particular examples always begin with a. So you basically had to use a to the I if you want to cancel stuff at the beginning. Any ideas for this one? Yeah. Yeah, how about BA in parentheses to the power I? This will cancel, come on, BA to the I. I like that. And then can you say what's the resulting language when you do that?
BA to the n minus I, AB to the n.
Yeah, great. BA to the n minus I, AB to the n. And again, these are all different for different i's, right? For I equals 1, you have one fewer occurrence of BA at the beginning than there are ABs at the end. For I equals 2, you have 2 fewer BAs than ABs, etc. All right, so these are all different. So L is not regular. Great. So your job in these problems, I mean, usually these are fairly simple, but you have to just sort of look at, usually you're going to look at the beginning of the string and decide what exactly am I going to cancel off in a convenient way using the derivative. All right, I got more. I got 99 problems here. How about, here's another sort of simple, you just kind of have to see these once to figure out what you should do. How about this? A, B to the n, A to the n. This one is weird because we have like one stray extra A at the beginning. But otherwise, we want to do the same basic idea here. Anybody got a plan for this one? Yeah?
Do like dA and then B to the I?
Yeah, derivative with respect to a b to the I. That's great. I think his idea is you got to cancel that first a first to sort of get to the chewy insides, and then you cancel a bunch of b's, all right? That a at the very beginning is just blocking you from the good stuff, which is the b to the n. So I cancel the a at the beginning, followed by some of the b's that follow it. And then what is the set that you get when you do that derivative?
B n minus I a n.
Yeah, b to the n minus I, a to the n. We cancel the first a plus some of the b's. And then again, you know, just like all the other examples, these are all different for different values of I. That means L is regular. These are all different. I mean, did I say regular? I mean non-regular. So L is not regular. Sometimes people say irregular. I mean, sometimes students in this class say irregular, although that's for what, I don't know why, but people don't say irregular. So don't say irregular. It's just not regular. All right. Okay, how about, I got more. How about, well, this is kind of similar. A to the m, b to the n, c to the n. Actually, this is not kind of similar. It looks kind of similar, but it's a little, there's something a little subtle about this. So now, instead of, in the previous example, we had just a single a at the beginning, which you had to get past. So I did the derivative of the a first and then a bunch of b's. Now I have a to the m. So we have now just sort of a bunch of a's at the beginning. All right. I think there is an obvious answer here, or an obvious thing to do when I choose the d's, which turns out to not really work properly. I think the obvious idea would be this. You cancel, first of all the a's and then get some of the b's. All right. This actually, maybe you shouldn't write this down, because this actually is not quite going to work properly. This, I will say, you can't do that. Since m is a variable, it's not a specific number, right? Really, like when I write a set like this, maybe I should, if to be more specific, what I mean is it's a to the m, b to the n, c to the n such that m is a natural number and n is also a natural number, right? So m is not a specific value. It's not like m equals 2 or something, and you can just stick that here. So this is ambiguous when I say this because m is a variable. It's not a specific number, all right? So this is not quite going to work. Just because, I mean, I get the idea of what you mean by that. You want to cancel the a's first and then continue to cancel the rest of it. But that, specifically writing it that way, is not going to do it. A better idea. This is a better idea, which on the surface seems like a terrible idea, but actually this is the way that you have to do this kind of problem. Check it out. Just that. d(b) to the I. I'm just like in denial about the a's at the beginning here. I'm pretending there are no a's at all at the beginning here. All right. What does this do? If you take the derivative with respect to b's only, remember the way that this derivative works is you look at all the strings in here which start with b's, and then you cancel out some of those b's, all right? If the strings don't start with b's, you just throw them away entirely. This is the way that the derivative works here. Now, in this language, actually most of these strings begin with a, right? But m being a natural number, m is allowed to be 0. And so some of these strings actually don't have anything at the beginning, and they do actually begin with a b, all right? So what happens here? This all strings starting with A get discarded. Only those starting with B will remain, right? And in our original language, some of them actually do start with B because our original language can allow the m to be 0, which means some of those strings actually don't have the a to the m part at all at the beginning. So only those starting with B remain. And then of those ones, you take off the first I B's, all right? So can anybody tell me then, what is the actual set that you get when you take this derivative here? You just ignore entirely any of the strings which started with A's. Of all the other ones, you take away some of the B's. Yeah? Yeah, she said b to the n minus I, c to the n. I like that. What happened to the a's? The derivative didn't exactly kill the a's at the beginning. It's just the derivative kills the entire string of any strings which actually started with a's. And only the ones that didn't start with a are the ones that we consider. And of those, you cancel some of the n's, some of the b's. All right? And anyway, now we conclude those sets are all different, right? Just like all the other examples. Now it looks the same as the others. These are all different. So L is not regular. This is, in my opinion, a weird example because you take the derivative with respect to something that you don't even see at the beginning of the strings. But it's because some of those strings actually do begin with B's. All right? I got more. I'm never satisfied. How about another one? This one actually is going to look very different. Let's try all strings x such that the number of a's in x equals the number of b's in x. This also is not regular. The number of a's equals the number of b's. This is different from a to the n, b to the n, because a to the n, b to the n has the same number of a's and b's, but they're all like, you see all the a's first followed by all the b's first. This allows for other things, like a, b, b, a has the same number of a's as b's. All right. What derivative are we going to use? Now, here you get no clues about what the string looks like. You have no idea what's at the beginning of the string, which makes this a stranger example. Usually we we look at the format of the string and try to cancel off the beginning by doing derivatives. It's not such a big deal. We're going to do this. And the reasoning is similar to before. Actually, you could do a to the I or you could do b to the I. This will cancel off the first I, A's, if they occur at the beginning of the string. If they don't occur at the beginning of the string, then you just throw those strings away entirely. So what this does is, when I do this derivative, I consider among strings in which the number of A's is the same as the number of B's, I think only of the ones which actually started with a block of A's, and then I cancel off some of those A's. And then I ask what remains after I canceled off those A's. What's the set that you get after that? So think about only strings that have the same number of A's and B's. And among those, only the ones that begin with a bunch of A's. Then you cancel those A's off. Can anybody say what kinds of strings will remain? They're ones where there used to be the same number of A's and B's, and they started with A to the I, and then you just remove the A to the I. What's left over? This is a little strange. Yeah?
Strings where the number of A's is equal to the number of B's minus I.
Yes, I think this is exactly what I was going to say. So this is x such that the number of A's is equal to the number of B's minus I. I think this is a little confusing to get it right. Should I have minus I over here or minus I over here? I think they used to be the same, but then I took away some of the A's. So now the number of A's is less than the number of B's. Specifically, I less than the number of B's. Yeah, I think I agree. All right. L consists of strings where they were equal. When I take this derivative, I consider only strings where they were equal and there were A's on the front. I'm going to get rid of those ones. And what remains is just some string where there are now I fewer A's than B's. And again, these sets are always different, right? When I equals 1, this means there's 1 less A than B's. When I equals 2, there's 2 less A's than B's. That's different. Okay, so these are all different. And so L is not regular. These is all different. So L is not regular. All right. This is a little weird. I got just a few more, and then I have some for you to try. How about, this is very similar. This was number of A's is equal to the number of B's. How about the number of A's is less than the number of B's? Number of A's is less than the number of B's. This one is, I would say, slightly more confusing, but you can still do basically the same thing. So I'm going to do, let di be the derivative with respect to a to the I of L. And now I'm imagining only the ones which started with a bunch of A's. I take those bunch of A's away, and what remains is a string in which now the number of A's, like it used to be the number of A's is less than the number of B's. Actually, now the number of A's is like even more or less than the number of B's. You can say it like this. Now I can say the number of A's is less than the number of B's minus I. This is actually exactly the same as the previous example, only I'm using a less than sign rather than an equal sign. But actually, it's a little more confusing, but all the reasoning works exactly the same way. Now it's not that the A's is less than the B's, it's that they're a lot less, like I less. So if I is 1, it means it's at least 1 less. If I is 2, then it's at least 2 less, and so on. All right? Anyway, I finish in the same way. These are all different. And so I is not regular. So L is not regular. Sometimes people ask me, do I got to write that every time at the end? Because it's like I wrote exactly that same sentence every time at the end. My answer is yes. Just write it. I don't know why. Sometimes in math classes, people are like, I do not want to write anything unless I absolutely have to. Don't make me write an English word. Come on. Just write it. Come on. That's what I say. These are all different, so L is not a regular language. All right? Any thoughts about that? I got 2 more, and then we can all try some. 2 more that are a little more complicated still. How about x squared? Let's say x is in AB star. This, we haven't really talked about a language like this before, but this is the language of all squares. That is just any string which happens to be the square of some other string. So for instance, this would include something like A, B, because you can break it into 2 parts, which it is a square of something, right? Or, B, something followed by something. That's what, something followed by the same thing. That's what this language is. All strings that you can sort of break into two halves, where the 2 halves are the same as each other. All right. What can we do here to take the derivative? Again, the format of the strings does not suggest at all what they start with. And so in that situation, usually you just want to do something like this, where you just only consider the ones that start with A's. I used A. There's nothing special about A here. You could use B if you want, but I'm basically always going to use A. So I'm going to say, it's a little less clear what's going to happen when you do this, but this is my strategy. I have no idea what these strings begin with, but some of them do begin with a bunch of A's, right? And so I can take the derivative to cancel those bunch of A's. We have to think about what will remain. What do the strings look like after you do this? I'm going to sort of fill in the blanks here. Maybe, I'm not going to call it X anymore, but what do the strings look like after you cancel a bunch of A's? So I'm going to try and do a little sidebar here. We imagine strings like x squared, which begin with a to the I, right? These are the strings that we are concerned with when we are taking this derivative. So those strings, actually, they look like they begin with a to the I, and then they have some other stuff. But since they used to be a square, you can say they must look like this, right? These are strings which are squares, where they also begin with a to the I. So strings of that format, they should look like that. And then what remains, now it's clear if you realize all the strings have to look like that. What remains when you cancel the a to the I on the beginning? Well, you just get the rest of that, the sort of the yay part. Y, a to the I, y, right? If I cancel this part, when I do the derivative, that guy gets canceled, and what remains is the rest. So this actually is what this set is. Y, a to the I, y, such that y is any string. All right. This is really, in my opinion, not obvious at all, but you have to think this through a little bit to figure out what is the format of these strings after you cancel out the thing on the front. And it looks like that. And now I ask you, are these all different from one another? And I say yes. Like this DI is strings which have something, then a to the I, then something else. So if I is 1, that means it has one A in the middle. If I is 2, it has 2 A's in the middle. That's different, right? So I am, again, going to say, as always, these are all different. So L is not regular. All right. I got one more similar, and then I would like for you to try some. How about this? This R here means reverse. XR means reversed. So you take the string and just write it in the opposite order. So this is kind of like x squareds, but it means these are strings where it has one part followed by the reversal of that same thing. So for example, BA, BA, A, followed by AA, BA, B, right? That's the X reversed. So that's what this language is. It's like the x squareds, only you're reversing the second part. All right, let's try and do a similar trick as we did in the previous example. Again, we don't get any clues about what the x looks like, so you might as well just do the derivative with respect to the ai. Derivative with respect to a to the I of L. And then what is that going to be? Again, we have to think about strings of this format which begin with a to the I. So strings in L which begin with a to the I look like well, they have a to the I first. You know, I'm trying to look at this format, but I imagine that the x part actually starts with a to the I. So it's going to be a to the I followed by some other stuff, like that's the x. And then what's the rest of the string going to look like? It should be the reverse of x. Yeah?
Y, a to the I.
Yeah, something like that. That's actually not exactly right. Anybody have a slight amendment? I want this is supposed to be the reversal. I wrote it in the other order. It's true. Yeah?
It would be y to the r.
Yeah, it should be y reversed, a to the I. If y has more than one letter in it, then you're going to have to reverse the y. Should I also reverse a to the I? I suppose yes, but you get the same thing again, right? A to the I reversed is the same as a to the I. So this is what the strings look like. And then when I take the derivative, I'm going to cancel the a to the I at the very beginning. And what remains will be the rest of that stuff. So what remains when I do the derivative is y reversed, a to the I, where y is any string. All right. And so what you have is di is all strings of that format where it ends with I different copies of a. And these are all going to be different. D1 has one a at the end. D2 has two a's at the end, and so on. All right? All different. Any thoughts about that? This is a little tricky. They seem very simple at first, but they can get a little more complicated. All right. I got a few for you to try in our remaining 10 minutes. So your job, show that all of these are not regular. All right. So this will be this first one is very straightforward. The others are a little more interesting. So that last one is x followed by x bar, where x, the alphabet in that one is zeros and ones, and the bar means not. That is to say, when you do the bar, you just change every 0 to a 1 and change every 1 to a 0. But you keep them in the same order. All right, see what you think. We got 10 minutes. I will give you a moment and then walk around and see how you're doing. when you do the derivative, it only cancels on the beginning of the string. It looks like you're canceling the right.
So it would just be B.
Yeah, just don't be clear.
But then would that affect this B also?
No, it wouldn't. Doing okay? Yes? Great. Alright. Mm-hmm. I think here, that should put that there. Because, like, I understand that you want to put it there because it's in some days.
Yeah.
But
Also, so that, it's actually, it's correct to not have that there.
and it's like this, which means the n is much less than that. If you do both ends, too much. Doing okay?
That's good.
Like the others are a little harder. Doing all right? Mm-hmm. Yeah, it looks good. How's it going? That's good? Yeah. This should be it. Is that a 1?
Yeah.
I think we should be using i's. I think you meant I here, e to the I. You can't put n here because n is a variable. Well, we got 5 minutes. Let's talk about these. I know not everybody is finished, and that's fine. I didn't quite give you enough time. The first one, as I was walking around, pretty much everybody got the first one correctly. You should say, so for the first one, b to the n, a, b to the n. This is L. You say let di be the derivative with respect to b to the I, because these strings begin with b's, and you want to cancel some of those b's. And what you get is b to the n minus I, a, b to the n. And those are all different for different values of I, because they have I fewer b's at the beginning than there are b's at the end. These are all different. I think pretty much everybody said that as I was walking around, so good job for that. The other two are more difficult, in my opinion. So the next one was a to the n, b to the m, where 2n is less than m. Is that right? Yes. So for this one, they start with a's, so it should be your natural sort of impulse should be to do a to the I, because these derivatives always cancel what's at the beginning of the string. So without really thinking about it, you should probably lead yourself to the derivative with respect to a to the I. You'll have to think about it, though, to write down what actually is, what do you end up with after that? Here's the way, there are a few different ways to think this through, but the way that I would think of this is, what it begins, like at first, what you have is some number of a's and then some number of b's. After you do this derivative, you have, it's still going to be some amount of a's and some amount of b's. It's just that you just decrease the number of a's by I, all right? The way that I would write that is something like, it's still some number of a's followed by some number of b's, but it's even less than it used to be, right? I took away I of the a's. How can we say that? I think that's this. 2n is less than m minus I. There's I less than there used to be before. Now, maybe it should be a 2i there. Anybody think this through clearly, more clearly than I did? What did I write on my paper? Now that I'm seeing this, I'm confusing myself. I didn't write the answer on my paper. I thought it was too easy for me.
Did the plus I after the n?
You put plus I on the other side. Yeah, so, okay. This is the same, right? You can add the I over to the other side if you want to. Those are the same inequality. Yeah.
How is it still, because isn't it still true that it's still 2n less than m? Like, doesn't it still hold true? So couldn't you just write, like, isn't it always going to be that 2n is still less than m? So wouldn't the original language still be true? Like, couldn't you still write that?
It's more or less than it used to be. So this, for instance, 2n could be 1 less than m, but when the I is here, it has to be even more than 1 less, right? It has to be I less. I took away some of the n's. All right, so you could write it this way or this way. Those are equivalent. Anyway, these languages are all different because of this I right here. If the I is 1, it means it's less than 1 less than m. If the I is 2, it's less than 2 less than m. Those are different languages. This is confusing, but that's how we do it. These are all different. And in our one remaining minute, can we do the last one there? That was the one about the x followed by x bar, which is, my pencil's going out right at the end. This one you have to handle kind of like the x squared, so the x followed by x reverse. So you think about, I'm going to do the derivative with respect to 0 to the I, or you could do 1 to the I, however you like, of this language. What is it going to be? So remember, we have to imagine that those strings, they did begin with 0 to the I. So this is how I would have written in the other ones. Strings in L which start with 0 to the I look like 0 to the I followed by some other stuff. That's the x part. And then here I want to write the x bar part. What does the rest of it look like? Anybody think this through? Yeah?
1 to the I, x bar.
Yeah, it looks like 1 to the I followed by y bar. That's what you get when you flip all the bits, as they say in the computers. All right? And so this derivative looks like this, but you have canceled the 0 to the I at the beginning. So it looks like y 1 to the I y bar, where y is in 0, 1. And these are all different. All right, the end. So some of these are easy. Some of these are quite a bit more complicated. That's how it goes. All right. Sorry I went over by